In this video, we're going to be looking at using the trapezium rule for evaluating the integral between an upper and a lower limit of a function which cannot be integrated algebraically. So if we draw a graph of a potential function, I've shaded there the area that we'll be looking to find. We divide the area up into strips by drawing lines so that we have equal width strips across the entire area. In this case, we've created 5 strips. This method will be a refinement on the previous video because instead of creating rectangles, now we create trapeziums by joining across the tops of those strips as shown. And we can see immediately that although this will be an underestimate for the area underneath this curve, that it's likely to be much closer to the real area than by the method of using rectangles. We can add the y-coordinates of the sides of those trapeziums. Starting from the left, you would have y0, y1, y2, y3, y4 and y5. Because we have 5 strips, the width of each strip will be the upper limit minus the lower limit divided by the number of strips, in our case 5, and we call that h. Our approximation for the area under the curve will be equal to the sum of the areas of those 5 trapeziums. So if we begin with the first trapezium, and remembering that we add the 2 parallel sides, so for the first trapezium it'll be y0 plus y1. We want half the sum of the parallel sides times the distance between them, and that's the area of the first of those trapeziums. The second would look very similar. This time though it will be y1 plus y2 over 2 times h, and we can go on to do that for all of the trapeziums that we have. And so we have the third, the fourth and the 5th trapezium there. Each one of those areas has a common factor of h over 2. And then for the first trapezium we'll have y0 plus y1, and then y1 plus y2, y2 plus y3, y3 plus y4, y4 plus y5. Looking at the larger bracket, we see that on the left y0 and on the right y5, they only occur once, but y1, y2, y3 and y4 all occur twice. And this enables us to collect all those like terms together within the bracket to give an overall answer as shown. So that we have h over 2, and then in the bracket we have the first y0 and the last y5 plus 2 times all the other y coordinates. And we can now generalize that idea and say that if I have a function and I want to integrate that between a lower limit of a and an upper limit of b by dividing it into n trapeziums or n intervals, then the trapezium rule would look like this, where the integral is found by doing h divided by 2, and then inside the bracket y0 plus yn, the first and the last y coordinates, and 2 times all of the others, y1 plus y2, all the way down to yn minus 1. And h in that formula, remember, the width of each trapezium is the upper limit b minus the lower limit a divided by the number of intervals or trapeziums. The significance of this shouldn't be lost. We're trying to integrate a function, which is in itself a very difficult thing to do. but we've reduced the evaluation of that integral into just knowing y coordinates and the width of the trapezium, and those are all easy things to find, and we can use our table function on the calculator to help us with this. Here we come to an example, and I've selected for this first example an integral that can be done exactly. And then we're going to do it using the trapezium rule with just a very small number of intervals. And then to show just how valuable this method is, we're going to calculate the percentage error. It would be a good idea for you at this stage to pause the video and to go away and have a go at integrating this function yourself exactly and see what you come up with. How did you get on? I wonder if you used the rule of powers to rewrite what we have as half the ln of x dx. And some of you may remember what the integral of ln x is. If you don't, this is one that we would do by parts. We would say that u is equal to ln x, so du by dx is equal to 1 over x, and dv over dx is equal to 1, so therefore v will be equal to x. We've got a common factor of a half, which we can take out, and then we're going to write uv. I'll reverse the order and write vu for convenience, and then minus the integral of v du by dx. And remember, all of that, both the x ln x and the integral that we haven't completed yet, is going to be evaluated between 1 and 3. And that then becomes a half x ln x, and when the two x's cancel in that expression above and I integrate, I would just have x. So plugging in my two values, I'll have a half into 3 ln 3 minus 3 minus 1 ln 1 minus 1. The ln of 1, you'll remember, is equal to 0, and so when I put all of that together, I will end up with a half of 3 ln 3, and the minus 3 minus minus 1 becomes minus 3 plus 1, so minus 2. And when I evaluate that as a decimal, I'll get 0.647918, and so on. So it's in part B that we begin to use the trapezium rule. We begin by working out our value for h, which is the width of each trapezium, and that's going to be equal to the upper limit minus the lower limit divided by the number of trapeziums or intervals, in our case 4, and so our value of h is 0.5. This value of 0.5 dictates the way we lay out our table, where we're going from 1 to 3 for values of x, going up in intervals of 0.5, as shown. We could now use the table function on the calculator to populate that table for y values, but in this case they're easy enough to write and to enter just as they stand when evaluating the trapezium rule to find the area under this curve. At this point, pause the video for a moment and have a go at setting out all of this in the trapezium rule to see if you can get the correct structure. How did you do? It should really look something like this. Now you may have put your final y value ln root 3 at the end, but we've got 0.5, our value for h, divided by 2, And then inside the big bracket, we've got our first and our last, and then 2 times all the other y coordinates. And when we enter that into the calculator, we get a value of 0.64105, and so on. Finally, we were asked to find the percentage error. And to do this, we need to work out the actual difference between the true value and our estimated value. Well, the true value is bigger than the value we found by the trapezium rule, and so we do the true value, take away 0.64105, and so on, dividing by the true value, 0.6479, and multiply by 100 to turn it into a percentage, and we get 1.0597%, a little over a 1% error in our calculation. In this case, because we calculated exactly the area under the curve, we could just by looking see that this is an underestimate. But very often you'll need to do some curve sketching to determine whether your trapeziums are going to be an underestimate or an overestimate for the area that you find. In this example, there wouldn't be any possibility of working out the exact value for this integral, and so we're just going to have to use the trapezium rule. As I mentioned before, it's a good idea to sketch the curve so that you have some idea of what's going on, and here is the curve for our function. And here I've very crudely sketched on the trapeziums that we would be considering. The nature of the curve would seem to suggest that the area that we calculate using the trapezium rule is likely to be an overestimate of the actual area that we are concerned about underneath this curve. As before, we begin by calculating the value of h. So in this case, it's going to be 1 take away 0 divided by 4, 0.25. This dictates the way that we lay out our table, which is going to go with values of x from 0 to 1 in intervals of 0.25. This is a case where it would be a good idea to use the table function on your calculator to give you the corresponding values of y with the values of x that we've got in the table. And finally, we're in a position to evaluate our integral using the trapezium rule. And all we need to do is to put all the pieces in the right place. So we begin with h, in our case 0.25 divided by 2, multiplied by, we want the first and we want the last, 0.5215, and then we want 2 times all the other ones, 0.6678, 0.5908, and 0.5477. And plugging those numbers into the calculator, we get a final answer of 0.64176, and so on, which simplifies to 0.642 to 3 significant figures.